Up to now, what I've been talking about is really about analysis. There hasn't been any synthesis of any new ideas, but analysis, I kind of want to emphasize, I believe it's important because when you're able, for example, to mapping between a particular way of modeling, like the probabilistic energy-based models, to autoencoders, you can actually identify what are the common elements to both. What are the things that actually make things work, as opposed to, instead of having an argument of probability versus a neural network, we can maybe identify that what really makes it work maybe to square the units and do normalization and so on. So I think, or when we say go from the k-means feature, the threshold features, to sparse coding, there again, everything that we know about sparse coding can now be used to understand better the threshold features. And then also that enables us to understand why it might be that the rectified units are working well on the deep autoencoder networks. So I think that's analysis essentially for that. Synthesis is also important. Generating new ideas is kind of more fun. Analysis is kind of tedious. You have to get paper and do the work and so on. With synthesis, you just like, let's build something new and cool. And I think the majority of people here in this room tend to be, I think that's one of the things that attracts people to this field. So the next part of the talk, I'm going to talk about synthesis, building systems to do deep learning. But in doing synthesis, I think it's important to first understand what the problem is that we're trying to solve. Image classification is one of them, and many of the talks here have been about image classification. But like Roland was pointing out, there are many other problems that are also very important, just in vision, like being able to know what a plane is and so on, without having to do image classification, being able to track objects and so on, it's sort of essential for survival. And I would argue, and many people have argued this before, like in particular Dana Ballard, who's done some amazing work in computer vision throughout his career, that vision to a large extent is not just about object recognition, or it's not about image classification. And I will show you some videos that sort of illustrate that, and these videos actually come from his lab. I think his wife Mary actually did this video that I will show you. But I'm going to start with, and you've probably seen this a lot. If you've seen this, so let's see, how many people have heard of change blindness? Okay, so if you just stay quiet, let the other folks enjoy this. So I'm going to show you a video of two images alternating. There's sort of a gray sheet in between, but there'll be two images alternating, and then your task will be to tell me what's the difference between the two images. But just don't say it loud once you see it, but rather, I don't know, put your hand up if you want to say you've already seen the difference or whatever. Let others enjoy. And this is in no way a test of IQ. Some people often think of. Okay, there's the two images. As I said, there's a difference between the two images, and it's quite a lot of pixels that are changing. Probably 20%, maybe roughly, no, a bit less. Maybe 10% of the pixels are changing. And it's something that also has semantic value. So how many people have seen the difference by now who didn't know this? Yeah, but don't say it loud. Hopefully you didn't hear that. It's something that airplanes need to fly. And if you still haven't seen it, it's the engine, as someone pointed out. Wow, you think you see it all, right? Yeah. And so this is called change blindness. It's the same thing as if you go to YouTube and type gorilla change blindness. You will see a lot more you'll be subject to many more interesting of these videos. So it shows that we do pay attention to certain things, and if the right distractors are there, we will not see certain things. Okay. Now, the following video that I got from Odd at MIT. Hang on. There is this other one from right here, Southern California, from Laurent Itty's group. Is showing some gazing. And what Laurent does very nicely in this video is that he actually, he shows the blind spot, and then he's showing exactly, he sort of simulated like what would be the foveations that you would get. I'm not exactly how he's done that, I guess he's computed the distance to the screen and so on to decide how much to blur. I mean, the point being, our vision is not this HD thing, 360 degrees that we believe it is. Okay. Now, this is the one that comes from Odd's lab at MIT. And so change blindness, some people think is trickery and so on. You're just distracting attention. This will illustrate something else. So I'm going to click somewhere to begin, and then please follow the instructions on the screen. All right. What do you guys think changed? Pardon?
The building.
Someone noticed the building. Note, this building right now is pink. Okay. With a sign, pink building with a sign. What else changed? The car? Maybe. There's a maybe there, not so. Yeah, there was a pedestrian here, it's gone. And detecting pedestrians is very important, as we've learned in a few other talks. What else? There are certain things about this image that also make us think that something has gone wrong. Like the wrought iron here is broken. So you can see it's like photoshopped. There's these brown doors. This door is green. Okay, so no pink building, no pedestrian, green, brown doors, and doors up here. So it makes you wonder why they're there. The original image was this. And if you are like everyone else, you will probably be saying, that's not true, do it again. So I'm gonna do it again. So now, see, now we have the window, we have this brick building, the pedestrian is back, the door is brown, not green. The car's, I think, the same. But I could be wrong, because every time I think I've seen it all, someone points out to me, it doesn't matter how many times you watch this, there's stuff you still miss. So let's close it and open it one more time. And now if you focus attention on one thing, like the building, oh wait, yeah, you see it's changing. Right? But you do have to focus your attention there. Because this is what it's showing, is that if you were to store everything in your head, you would probably been able to do a diff, and you would have been able to see the differences. But you don't, because our brains are finite machines that live in the real world. They can't store all the video that's incoming. And so we use gazing and attentional mechanisms, and we also focus on what things we think are important. When you're hiking and all of a sudden you see, a cougar approaching, you sort of keep an eye on that cougar. You don't look at the flowers and stuff like that. Now, this is the one now from Dana Ballard's group. So this basically shows you fixations where you're looking when you're doing a task, like in this case, making a sandwich. So your eyes fixate basically where you need to fixate to solve a task. Do I have a good grip? Where is the bread to put and then you focus where you put the bread. You pay attention to the grip. Then you put peanut butter. Lots of yummy peanut butter. It kind of makes me hungry. Okay, make sure look at the edge of the container so that the jelly doesn't fall over. The eye is doing things that make common sense. The fixations make sense. There's a guy from that lab here. Do you really make your sandwiches like that? Texas peanut butter sandwich. So this part is very interesting. So when Dana showed this to me the first time, I was amazed at how your eye fixates on the edge of where the liquid is. Because when you're pouring, what you care about is not overflowing. So you pay attention to that. So all that happens without you ever introspecting into it, without you ever thinking about it. Okay, so we've heard about dorsal ventral streams. This is the dorsal stream that's doing vision that's related to action. Some people actually prefer to call it the what and the how streams as opposed to what and where, because one is about how you perform actions, and it seems that we can't we don't perceive. It seems to be something that it's outside perception, because actually perception is a very loose word. It's more we're not aware that we are doing those tasks when we're doing them. For this reason, I think it's very important that when we do computer vision, that we actually, at some stage, gather some eye tracking data and look at what the data really looks like, because that data will tell you a lot about how vision actually works. And you can't just by introspecting, we can't just sit here introspect as to this is how we believe we see the world, because we're not being conscious about how we see the world. And so I think it's sort of important to do this sort of eye track. I actually have a bunch more videos on this, but I just can't play them. We don't have the right codec, so I was having some technical difficulties. But these videos show people walking in the forest. And when you walk in the forest, I think Andre played with that data. There's sort of, you believe you're going for a nice hike and you're seeing the little hummingbirds and the trees and so on. But actually, most of the time, you're just using your eyes as a cane in the path to make sure you don't get off the trail. And it's really amazing. It's just like you would imagine a blind person going with a cane and then looking at the stones to make sure you don't trip yourself. And so most of the time you're on a hike, your eyes would actually fixate just on the task of not leaving the path. All right, so that sort of work, especially when I first saw a talk by Dan, it got me interested in attention. And I started like wondering, how does the eye actually sort of move, and what are the principles that decide where we move the eye and so on. To this day, I don't know the answer to that, but let me tell you about a few things that we've done, and now in terms of synthesis of algorithms. The first thing to try is the most obvious thing, which is to do, like everyone else, this convolutional pooling architecture. But because we have dynamics, we now need to do things over time and over space. So we have some spatial pooling, we have temporal pooling. Historically, we were motivated by some work that Jeff Hawkins was doing, where he separated these two pooling operations, and so we were alternating. But of course, you could actually just think of it as cubes in 3D space, I guess 4D space, and then try to pool. And you know, each of those green boxes is your typical convolutional architecture where you move a window and so on, and you use several filters. And by doing that, we actually learned these temporal filters, which not quite as nice as, whoops. Unfortunately, okay, so you see like for example here, it's an edge moving to the right, and so on. Now, my hope with this was then to do the following experiment. To take some gazes of, so there's a sort of a pedestrian, but what I would like to do is just take gazes of the pedestrian and try to see that if we had this convolutional model that's looking at things over time, just looking at gazes over time, can this convolution model then sort of imagine the world as we see it? Be able to do reconstructions. So my hope was to then do this sort of spatio-temporal completion of the scene. To, like, if I'm looking at this right now and someone asks me the question, what shoes is this person wearing? Then the intuition was that because I can predict where the feet are, I would be able to quickly navigate to where the shoes might be and then identify what the shoes are. Okay, again, this is a small video here, but the idea here would be you would be dealing with an HD video, which you would not be able to just use an autoencoder taking, a 5,000 by 5,000 image, because it would be too expensive. So you really would need to fixate. The problem with these convolutional pooling architectures, as we've heard before, is you're getting invariance as you go up by pooling, but when you go down, you can't reconstruct the image very clearly. So you get these fuzzy images when you go down. There's been more recent work by the folks at NYU that allows you to keep track of which unit you're selecting when you do max pooling and so on. And conceivably, if you were to keep track of that, then you would do better reconstructions. Instead, we took a different approach, which is more of an engineering approach. And this is sort of now the last part is the Bayesian part of the talk. So we took an engineering approach based basically on Monte Carlo and Bayesian methods. And so this is what I'm going to show you. I'm going to show you some videos illustrating first what the system does, and then I will discuss what the components are. But what the system does is you have an HD image. So these are all MNIST digits, but now MNIST HD and several MNIST. And your task is not to just recognize whether this whole image is an 8 or a 3 or a 4, but you actually have to find out where the 8 is. You have to first detect the object of interest, and then you can apply a classifier in this window to predict whether it's an 8 or not. Now, for practical reasons, the way we do detection is as soon as an object enters the scene, we're essentially looking at optical flow. we just put a huge window around the optical flow. We don't know exactly what the object is, but by putting a big window, you hope that you're going to capture the object. And so then what you need is a technique that will allow you to then focus exactly on what the object is. So there's big world HD, then there is still big world, which is the window around the 8, and then there will be smaller windows, which I'm calling Gs, as in gaze, G1 to G9. And these are the small windows that I'm going to first illustrate this with a discrete case, and then we'll go to a continuous case. In the discrete case, let's assume we have only, say, a template that has 9 windows. One window is active here. So think of this as your current fixation. And so when this window is active, this is the image that I see. So high resolution in the middle, lower resolution toward the end. So right now, the input to an RBM would be this. The RBM from this signal has to predict whether it's seeing an 8 or a 3 or whatever it has been trained to do. I will assume that the RBM has been pre-trained, so I already know its weights. But then I'll come back to this question at the end of the training. But for now, all I care about is when this 8 enters the scene, I want to track it. And then I want to figure out of all these windows, which are the windows that are more useful for actually identifying, keeping track of the object. My objective is to have a good track, to minimize the uncertainty as to where this guy might be. And then the other things the video will show, it will show something that I will be learning, which is how probable is each of these boxes, what's the best box out of the 9 boxes to track the 8. And then it will also, once you identify what it is, I'm going to be doing the classification. I'm going to be able to determine what digit I'm following. Okay, and so let's see if I can do this now. Oh, there we go. So now I'm actually doing here several objects. And this, again, is the big window. And in this case, I'm illustrating what I just talked about just for the 3. I'm gazing around. More often, I'm focusing in the middle. By saying I'm focused, I mean the algorithm is focusing in the middle. And this is what the RBM is seeing. These are the filters. And so it's learning a classification of it's learning a probability as to which, or what we call a policy as to where to look in order to classify that into in order to keep track of that thing. At the same time, it can also do the classifications. So there's a few more videos which will illustrate the classification. An interesting thing about this is that there's occlusions, as some of these guys are going over some of the static digits. And note the differences in scales, and note that the scale is changing dynamically. And that's one of the problems we have to deal with in real data. Scale changes, location, and so on changes. Okay, and then, of course, in Canada, people are obsessed about hockey, so we always have to track hockey players. It's a way to get grants. Okay, so that's a sort of a demonstration of the kind of system that I want to build. And now I will actually tell you how we built this preliminary system. Okay, so we have our HD signal. Our signal is just not 28 by 28 or even 100 by 100. It's actually much larger. It's your big screen at home. And all we're going to get is a foveated image, and that foveated image then could be passed into, say, an RBM to give you activations, and we're going to assume that we have these beautiful filters that have been pre-learned, and these are actually Marco Aurelio's filters. Now, the first thing is the model will evolve over time. And so Hugo La Rochelle and Jeff Hinton came up with this very nice model called the multifixation RBM, which allows you to have several fixations. The location as to where you're looking at in the world, where the fixation is with respect to some frame. And then you use a factored RBM on each of these guys. And you append to get a vector of latent features. And then from that vector of latent features, you can do sort of classification. So this is, again, the temporal pooling that we were looking at before. But now it has this twist that it has the gating mechanism, which is saying where you're looking. So it's a very smart idea. And so, okay, so this is just to say that so far we've been paying a lot of attention at the Hubble and Wiesel experiments, but it's also important to pay, to keep in mind that in the brain also has cells doing all sorts of other things. There's like grid and place cells, which, at least for a rat, there's this cell that will fire at regular intervals as the rat explores a maze, for example. So there's a very nice periodicity here. And this is sort of important. I need, without visual feedback, I need to be able to close my eyes and walk and know that where I am, so I prevent myself from bumping into objects. And of course, as Thomas was pointing out, there's also retinotopic maps where you actually know locations in the world with respect to your retinal frame. Okay, so now, so that made us think that there's probably, and we don't know how the biological plausibility of any of what I'm going to talk about now, but it's certainly, at least it's one could conjecture that somehow the brain is keeping track of locations and scale and so on, that there could be the separate encoding that would allow you to deal with multiple scale and so on. And if not, at least we've aiming to solve an engineering problem. The engineering problem is tracking. So traditionally, tracking is you keep track of the position, x and y position of an object, its velocity in x, velocity in y, and there's standard linear models that the folks, especially that do radar and so on, have developed to track aeroplanes and so on. We're not going to follow that because the type of problems we encounter in vision are very nonlinear and multimodal and so on, so we can't just use the standard simple approaches. And I'm going to take a probabilistic approach, which is we have an initial unknown state. The state is the location of the target, say, or the scale of the target, or how much the target is rotated, or whether the target is in, I don't know, red or green. Is the target mating, or is the target doing something else, eating, or whatever, something that an animal might need to know in order to interact with the environment. And then at each point in time, you get an observation. So now we're in the generative model, the same framework that Thomas was telling us about yesterday afternoon. And our goal is then, in time, estimate the probability of x given the observations up to that time. So the observations are essentially the foveations, and the x's would be the unknown location. In our work, you'll see later, instead of using the observations as the foveations, we're actually going to use the observations as the latent features. So we're going to assume that we've seen the world, we've gone, like following this, loosely speaking, the analogy with the brain. We first go to V1, we extract the features using the sort of a deep autoencoder, the deep RBM. And then once you extract those features, we're going to use those features to gauge where the location of the object is. Okay, and the hope would be that by working with features here instead of the data, you can do better. You can deal with invariances like small lighting transformations and so on, shadows, etc. As time progresses, you keep estimating the location at time 2, given all the observations and so on. This problem is called filtering or tracking. You can actually formulate it in closed form. But the problem is that it involves these intractable integrals again. Okay, so if we knew how to solve these sharp P problems, there wouldn't be any hassle. We could solve all of this. But once again, we need to deal with these sums that are very hard, that are intractable. And essentially this is the sort of the equations that you would use. So you would start with, there's a nice recursive algorithm for doing this. You have the filtering distribution at time t minus 1. You can, by integrating, by marginalizing over the state at the previous iteration, you can get the prediction. So you go from the observations up to t minus 1 to the prediction of where you might be at time t. So you predict what the location of the target is. And then you do a correction. So this is sort of predict, correct, predict, correct. Predict that this is going to be cold. Oh, it's warm, correct, and so on. And again, correction is just an application of Bayes' rule, but unfortunately, Bayes' rule requires that we know the normalization constant. So this is sort of optimal filtering or Bayesian filtering. And what we need to do is come up with algorithms that approximate these integrals. I will discuss now a Monte Carlo algorithm to approximate these integrals that's based on importance sampling, but you could also use other different kind of ideas to approximate these integrals. So if you know some very smart variational methods and so on, you could use whatever your favorite method is to solve these integrals. So that's not sort of central to this work. If you figure out how to model everything nicely with Gaussians, this basically solves. This integral becomes tractable, and in the linear Gaussian case, you get something called a Kalman filter. If these guys were all discrete, you would get what's called an HMM filter. So all those are just instantiations of this thing called optimal filter. Prediction and correction, sort of a very obvious thing as you're dealing with the world. As you go about doing things, you're always sort of predicting what's going to happen. Your hand is reaching for the door, and you already sort of know what texture and what temperature that handle is going to be. And if it actually feels like watery or whatever, then you get a surprise. So you get a sort of Bayesian surprise, and you're correct. Okay, with Monte Carlo, you've seen what the idea is. So what we're going to do is we're going to draw samples from the distribution at the previous iteration. And we're going to assume that those samples have weights, because essentially we will do importance sampling. And then if we have a weighted representation of the distribution, in other words, we have this blue approximation of the true function, which is red, via the samples, then we can replace the integrals by expectations. Okay? So that's essentially the basic idea. Replace the integral by a sum that is tractable over, say, n samples. Instead of doing like a Markov chain, when we draw one sample at a time, sort of like a depth type approach, we're going to use a breadth search type approach, which is we're going to maintain n samples in parallel, and we're going to update those samples each at the same time. So think of those n samples as n hypotheses as to where the target is. Okay? So you maintain hypothesis, and then by maintaining hypothesis, if it looks like the target is here, but then you get confounded and the target was really on the other side, you're able to handle things. So a typical example for maintaining hypothesis is the following. I'm walking that way. You probably were predicting I was going to come out of that way. You know, it's a peekaboo thing. But I came out this way. So the moment I go behind this thing here, you have to have two hypotheses. What is likely that I'm going to be going? And to adults, this is obvious, but try this with babies. If I have something that's occluding me and I go like this, we most often will predict that I will go like this, but sometimes I might go back. So at this point, your distribution has to have two peaks, because you don't know whether I'm going to go to the left or to the right. And that's essentially where probability helps us to maintain track of all these hypotheses. And so you have the way particle filtering, which is the sequential importance sampling algorithm, works, is you maintain all the hypotheses. At the previous iteration, you had weights, and it's a recursive algorithm. You propagate them, so this is the prediction step, and then you do this Bayesian reevaluation and you recompute the weights. The problem with this is that distributions are changing in time now. We're no longer in a stationary setting, IID, but now we're in a setting where we kind of have non-stationarity, where the problem is changing with time. And so, in this case, if you just do importance sampling naively, you might have a lot of these particles or samples will have very low weight, and some will have a high weight, and so very quickly the problem degenerates, and you end up with only one particle being active, and not being active in the interesting part of the distribution. A solution that was proposed back in 1949 is to actually pick the fittest particles and multiply the fittest and kill the unfittest. So this is sort of very much similar to genetic operators, you know. Do these, I don't know what it would map to. There's a mapping between each of these operations and things that people do in genetic algorithms, but this is basically go with the winners or survival of the fittest. And in fact, this algorithm has been reinvented multiple times, and in the AI community was known as survival of the fittest. It's been called particle filtering, it's been called bootstrap filtering, but it really is an old idea that's been used for 60 years or so. The code is extremely simple. You initialize by drawing from your initial location. You make predictions by sampling from this transition model, which is basically a model of how you evolve. Okay, so if you're at this if I'm at this location, you would predict that I could move in the neighborhood. You would not likely predict that I'm going to be doing this. Neither would you likely predict that I will disappear and appear here. Okay, and so that prediction model basically just telling you where you're likely to be at the next frame. It's constraining a search space. And then we have an observation model that tells us how you go from what you see, the image, to the location, to the estimate of where it might be. And so essentially we predict a new location, and then we evaluate how good that location is. And this is just a Monte Carlo implementation of the idea of Bayesian filtering. Prediction, correction, or prediction reweighting. And then we select the fittest. And this is a black box routine. Actually, that's just multinomial sampling. As an example here, suppose that this is my transition model. There's here a simple 1D case. And suppose I have an observation model that looks like this. And my goal is to recover x. Because of the squared operation, clearly there's two possible hypotheses for x. And also this distribution will be evolving with time, so the two hypotheses might at times merge, but sometimes they become separate. So if you want to, even this seemingly simple example becomes hard very quickly because of multiple hypotheses. The algorithm for it would be basically you take the transition model and you put it here. So for each sample, you propagate it through this transition model. You add noise to it. That gives you the new sample. And then the weights is just the likelihood in this case. So this is just a plain likelihood weighting algorithm. It's not going to spend much time in it, but it's easy to generalize the method to a recursive update where the weights, the incremental weights take this form, where you have, essentially we'll have the likelihood on top. Let me actually get the code. So instead of proposing from the transition model, you propose from another distribution, a proposal distribution, and then you reweight. If this Q had been the transition, then this term would have canceled with this, and we would have just likelihood weighting, which is what we had before. But this more general form of importance sampling allows you to choose a different proposal distribution, and then you need to compute this more complex weight. Why is that useful? It's useful because in computer vision, we often have many, say, heuristics. For example, we have very good face detectors and so on. So we can use those face detectors to construct distributions that sort of predict what it's likely that we will be looking, that the object will be in the image. And then this constrains that where the object might be in the image to what sort of likely locations, how things change over time. And then this further constrains it to the process by means of which you're gathering observations. So here's an example of this, exactly that idea. So here what I'm going to show you is tracking. Each of the white box is essentially, I think in this case, Kenji Okuma did this. I think this is just the posterior mean. And each of these boxes is essentially one of the particles that's predicting where the hockey players are. Okay? And so you're just maintaining those particles over time. And then you can do tracking. And then another thing, of course, is the camera is moving. So you don't know, this is always an issue. We don't know what the camera, whether it's the players moving or the camera moving. So if you have some reference frame, you can do some sort of homography to know exactly what's going on in the field. And this is sort of useful because then you know exactly where the player was, and you can watch the Olympics to get better demos of this idea. Now here, what we were using as the likelihood, sorry.
What about considering higher order models like this that you deeper into time, basically? Would that either further constrain the search space that you have to look, or does it make the problem much harder?
Oh, have longer dynamics, basically. It's possible to do that. And I think recently Kevin Murphy and Wei Lun, can't remember where they published this paper. I can give you the reference later. They've tried to construct better prediction models, transition models. Because often some of the images that we watch on TV, they're really low risk. I mean, like when we watch soccer in YouTube, the resolution sometimes is really low, and we still follow the game and so on. But at that stage, we're hardly ever using visual features. What we're using is our priors as to how objects move in the world to track. So constructing good priors, it's an art, and it's an important thing. For the observation models, here we were doing what a lot of computer vision people used to do in those days, which is just typically just use a color template. So basically what we were doing to determine whether where the object was we were just comparing the observation that so we predict a location in the image, we project a window there, and we would check the color. If the color was, say, top red, bottom blue, then we knew we were tracking, I don't know, a Spanish player playing soccer. But there was that course. The observation model was just based on color matching. And in the beginning, when some of this work appeared in computer vision under the name condensation, people were just using splines and fitting splines. And what I wanted to do here was to actually use what we've learned in deep learning to try to come up with better observation models. So you try to use richer models that would capture shape and that would also have nice invariance properties. Because just red shorts, blue, how does it go? Blue shorts, red t-shirt is not very robust when the lighting conditions are changing and so on. All right, so what we're going to do then is we're going to use deep architectures, but now my observations, so we're going to have a Bayesian model doing the location and tracking the location and scale and speed and rotation of an object. And then as observations, we'll use the output of, shall we say, loosely speaking, the ventral stream. So the appearance encoded through the features that we obtain using the multi-fixation RBM. And then our goal is to estimate what's the most probable location of the object. Okay, so here I was sort of going to illustrate exactly what we're doing with a cartoon, which is you have You have an image in time. You see an object in the image. Oh, and I'm a bit over time. I'll be done soon. You see an object in the image. You then let's assume that we've detected, for simplicity, let's assume we've detected in the beginning. The algorithms that I show are robust to this, but let's assume we know where it is at this point in time. And so what we do is we first predict where we believe this object will go. And predicting just basically means, so we predict the position, and then so let's say that this object actually ends up going at the next time frame here. And so what we do is we do a bunch of predictions as to where we think the object might be at the next point in time. So these are the particles, essentially. And then we check each of these windows to see which window still looks like a 2, still has the same features as a 2. And if we had the Google network, we would be able to do this very nicely, because it has the kind of invariances that we want, the minor invariances to lighting and so on. And what tracking is giving us through these transformations is invariance to scale and to location in an HD world. So this particle will get high weight. Maybe another particle here would also get high weight. And then these other particles would get very low weight, and they would be killed. And then we would propagate these 2 particles. And that's essentially what we're doing in this. And I'm using multi-fixation RBMs. But you could go and use any deep model. You could use an autoencoder for this. You could use your favorite model. At the end of the day, what we want is good features that allow us to tell that this guy here is still the same as this guy that I saw in the beginning. So we have that. I also, so that's how you would do tracking. That's enough. In addition, I'm going to do one more thing. I'm going to do control. I'm going to try to control where I gaze in order to, in this case, for example, be able to detect the object, localize the most important part of the object. So that adds another level of complexity to the model. And that's redundant. I mean, if you just want to do tracking, we're done here, we can stop. But if you want to sort of push it just because, then you need to estimate the belief state. You need to think of what action you're going to take that will change the location of the target. You need to think that you will have a reward. If you have the right belief, the reward will be high, but if you have the wrong belief, the reward will be low. Okay, so we create rewards in terms of beliefs. And then what we're doing is we're trying to choose the next action so as to maximize the reward. Okay, so we create essentially a sequential decision-making machine. We could now, this essentially looks like a POMDP. But instead of, it essentially is a POMDP, but instead of using the standard tools of RL, which are expensive, I'm going to use something a bit more myopic that I will describe in a bit. RL is great, and it solves very important problems in planning and high-level planning. But if I plan how to go home here, I'm not going to try to simulate in my head exactly what the color of the traffic lights, the sidewalks, etc. I'll have a rough plan. I know I need to go left and somehow downhill to get to my hotel. But the way I will do it is, as I will start walking, I will look at the world, and I will use the world to do computation and to do planning. I will see the red light, I will stop. I will see the pedestrian approaching me, I will probably step aside, and so on. So we need to use the world more when we're planning, just like that cane, like vision looking like a cane when you walk in the forest. Oh, and of course we aggregate over time, and then we get class labels as well. So the full model looks like this, and you could, it's very modular, so you could replace each component by your favorite component and run the same. The code's available online at Loris Bazzani's website. The whole algorithm is basically like a particle filter, but it has this extra control step. And you've already seen it in action, so I'm going to skip this. Of course, it can be used for other problems. And now let's go to the last step, which is the control. To do control, I use this technique called Bayesian optimization, which I think is very important. And we probably need to use it more because it not only deals, it can be used to solve the problem of how to choose the hyperparameters for a neural network, like how many neurons, how many layers, what should the learning rates be, what should the momentum be, should I use rectified units or should I use sigmoid units, should I use an autoencoder or an RBM? All these are discrete choices that could be parameterized, and you could have code that does all this for you. If you have the right reward functions, which is like cross-validation, which is what we optimize. So this is how planning with Bayesian optimization proceeds. So in this case, I'm going to do it in 1D because it's easier to illustrate than in 2D with an image. But basically, I need to decide location along this x-axis as to where to look next. So think of this as the big template, and I need to just, within this template, localize what the object is. Where is it better to look to localize the object? Now, I don't have an analytical expression for the function that I'm optimizing. That's the key thing. But when I try something, I get to evaluate that function. Okay? So I try something, and I actually find out whether that was a good thing to do or not. So I get a value back of how well I've done. I get an estimate of the uncertainty in the posterior, which is a Monte Carlo estimate. It's an expensive estimate, so I need to try to minimize the number of those estimates that I need to get. So fundamentally, I'm dealing with a problem of exploitation exploration. So, which goes as follows. Let's assume that we have two observations, this observation and this observation. I don't have the objective, but what I can do is I can approximate it. So in this case, the true objective is the dashed line. Of course, we never have it. So instead, what I do is I approximate it with this straight, solid line. Okay? Once I have this model, I have a model of what I think the cost function is in my head. And I've done it here with a Gaussian process, but you could do this with a Bayesian neural network, or James Bursher uses Parson estimators. Basically any your favorite regression technique you could use here. We're just constructing a surface. And then the other thing that we need is a function that tells us what is the next best point to try. And so what point to try next depends on two things. It depends of, based on our experience, what was better. So looking for something around here should be better than looking for something here, because this guy here has higher reward. I shouldn't explore the neighborhood of this guy because this guy is higher than this. It's doing better. So, you go with your best hypothesis so far. At the same time, you have to keep track of uncertainty. And this is where probability is very useful. Because if you don't know uncertainty, then you don't know how to explore. Uncertainty is important for exploration. If you're just exploiting all the time, then you just need a mean estimate. But if you need to know that there are parts of the space that I haven't looked at, and the amount by which you haven't looked at them, then you need to get the whole probability estimate. And if you combine, you can just take the variance plus the mean, combine them, and that essentially gives you this green curve. How you combine them, there's a few different ways. UCB, expected improvement, et cetera, et cetera. Thompson sampling, that's quite discussed at NIPS these days. It's just a variation of getting this. So right here, it's predicting that this is the point with the highest utility. And then this function is easier to optimize in many cases, because this one is just the mean plus the variance. And because you actually have an expression for this function, you actually have a function that you can approximate. So you can compute derivatives, et cetera. So you can do that very quickly. Once you find that point, and even if you miss the point at one time step, you could get another point that's not going to be that bad. Once you get that point, your uncertainty decreases near the data. The uncertainty is still high here, and it asks you to try a different point, and you get the picture. As you move, you actually locate the regions of maximum reward very quickly. Okay? And if you do that, that's essentially that's what's happening here. So this experiment as well as the theorem that I showed before connecting sparse coding was produced by Misha, who's sitting at the back. If you, this essentially illustrates the surface. These are the contours of the surface that I'm learning, the reward function. And it's learning where to actually focus your attention in order to track a digit. What's the best point to look at in this big window if you were trying to follow a 2 or a 3 and so on and not lose track? You could change the utility to not be about a tracking utility, but be about where to look in order to maximize classification accuracy as well and so on. But all those would be extras that you could play with. Some not necessarily trivial. And that's where to look if you want to follow JLo. All right, so that's pretty much it. So I'm going to end it here. And thank you all for being a patient audience and taking some of your time. It's been a great experience. I also want to not only thank the audience, but because I'm the last speaker, I think we should all thank IPAM and CIFR, the organizers, for creating what I think it's an amazing opportunity for all of us, not just only for the people attending in the audience, but also for all the presenters. I mean, it's been a great learning experience for me, and I think for many of us. Thank you.